So how to choose the coefficients? How to choose the coefficients AJ. And there are in general two ways, and one way can we probably manage today, the other one we'll discuss on Thursday. We do a two-step procedure. Where the first step is we generate molecular orbitals. Because in principle, these determinants, they depend on, in order to make the determinants, I have to choose orbitals. So the orbitals depend on there is some molecular orbitals, so they depend on molecular orbital coefficients. And in principle, I could vary those determinant coefficients, or configuration coefficients, and the molecular orbital coefficients at the same time. But in this procedure, we first do a Hartree-Fock calculation and choose the molecular orbital coefficients. So we do a Hartree-Fock to generate the molecular orbitals. And then we can make all those determinants from those. And in step 2, we find the determinant coefficients for fixed MO coefficients. So we choose the MO coefficients by doing Hartree-Fock, and then we keep them. So in all the procedures, in order to find those determinant coefficients or configuration coefficients, we don't readjust the orbitals any longer. We use the ones which we have. Take it or leave it. So we only play with those AJs. And then there are again two possibilities how we can now, for fixed molecular orbitals, we can find those coefficients. And one is variational. Or variationally. That's what we're going to discuss this week. And next week, we're going to discuss the other option. And that is by what I then will discuss with you, what is called by projection. And I hope that by the end of next week this makes some sense, what I mean by projection. But this is going to be Møller-Blessed perturbation theory and coupled cluster theory, whereas variational is configuration interaction. So this is, and variational then means, well, we have our energy. That's a function of those AI coefficients. Yeah, those are those. That's what we vary. How do we calculate the energy? If that's our wave function, how do we calculate the energy? Yeah?
An integral over the Hamiltonian.
Right, as what we would call an expectation value. So we take our wave function here. What's the symbol? I used phi. Okay, let's use phi. And they are, of course, a function of all those coefficients. We take our full Hamiltonian. No fooling around with the Hamiltonian here. And in case we forgot to normalize the wave function, or in order to make sure that while we vary the coefficients, the wave function is always normalized, we divide by the norm. And then variational means, because this is sort of the Rayleigh-Ritz variation principle, the best wave function is the one which gives the lowest energy. If you calculate the energy as this expectation value, then you can show, that's the Rayleigh-Ritz variation principle, you can show that the best energy, the one closest to the exact energy, is the lowest one. There's a lower bound. You can't get below the exact energy. So let's get so low as possible, and that means let's find the minimum of this expression while varying the coefficient, and that means we have to look at the derivative of the energy with respect to all those coefficients. That's going to be a lot of equations if we have a lot of determinants, and we set them all equal to 0. So taking the derivative of the energy with respect to the coefficient A1 means I have to take the derivative with respect to coefficient AI of my expectation value and that means in the first place I have to insert my expansion. Otherwise there's not much point taking derivative. So that's going to be the derivative with respect to AI. And then inserting the expansion, and I take the one where I don't distinguish between hard to fuck and all the other ones. So I get a sum over I here for the left one. Let's call that K for a second. So I don't have the same index as in the summation. So sum over I, then I get some coefficient, that's the PRA. I get some coefficients, and in principle that should be, so I get the coefficient out, that should be AI complex conjugate. Remember, everything in the PRA is complex conjugate. But we only want to treat real wave functions. So that's real here. And then I get determinant phi, I get the Hamiltonian, and then I get the ket. In the ket I have the same expansion, but be careful with the summation index, I have to use another dummy index, AJ now, so I get an AJ here, and phi j. And, unfortunately, the same story down here. I get in principle AI, AJ, phi I, phi j. Do I know something about those? Yes?
And they're also normal, so you only get the coefficients for the I theorem have to do the summation over I and j.
Well, that's true. So this is sum over IA squared. They're also normal. So the Slate determinants, they are normalized. Why are they? That's sort of the easy part. Why are they orthogonal? Yeah.
Because the spin orbitals going into the determinants are eigenfunctions to the Farthel's array.
And therefore they form an orthonormal set, as long as they're not degenerate. They form an orthonormal set, right? And they differ. They differ by having different orbitals in there. So there is always at least one orbital different. If I have two different determinants, there is always one orbital at least different between them. And that's the one which is going sort of kills the overlap. So the determinants are an orthonormal set, right? So we get down that in the numerator. Right, now we have to take the derivatives. And this is a ratio. So we have to remember good old quotient rule of differentiation. Let's start with the upper part. If I take the derivative now with respect to, I think I did it anyway with A. So if I take the derivative, this is also a product. So I get the derivative of first of this one, of this set, and then plus the derivative of that set. And if I take the derivative with respect to 1ak, that's one of them included in the set. So all the other a's, ai, where I is not equal to k, the derivative of those, that's a different one, that's 0. That's not the variable we look at. And then we only have the one where I is equal to k, but that's just a linear function. That's just the derivative of x with respect to x. That gives us 1. So we get either 0 or 1 taking the derivative with respect to the a's. But that's always only one of the summations, so I still have the other summation left. Because that's the derivative of this one, while I keep that one fixed. And that one is the whole sum, so I still have one sum left, and I get here corresponding case. In the numerator I get now a sum over j, aj, that's the second one. Let's do it step by step. And then I took the derivative of those with respect to ak, and all the other one gave 0 apart where I is equal to k. So I should have phi k h phi j. That's the first term of my product rule. Plus, now I keep the ai fixed, so I still have the sum over ai's, and therefore also phi I standing here. And I take the derivative of those, and the all are 0 apart the term where j is equal to k. Like this. Divided by sum over ai squared. That's still there. Plus, and then I never can remember the quotient rule of differentiation. So I always do it the other way around and say that this one is just to the minus 1. I can do the chain rule, but I can't do the quotient rule. So instead of having 1 over x and take the derivative of that, I rather take the derivative of x to the minus 1. Because that I can do. So let's see what that gives. Let's write that down there. I keep the numerator as it is, so I still have sum over I and j, ai, aj, and phi I Hamiltonian phi j. What's the time? Right. And then, as I have minus 1. So this is giving me taking that down. Is then here. If I take the derivative, I'm going to get a minus sign because it's in the numerator, in the denominator. And then again, I take the derivative with respect to ak, so there's one term surviving. But that's ak squared. So it's actually it's actually x to the minus 2 what I'm looking at, because all the other ones don't contribute. So I get minus 2 times a k and then I should get the whole thing squared down there. So I get sum over I ai squared, but I'd rather write that twice. For a reason which you hopefully can see in a minute. because now I want that part here. What is that? Yeah?
The energy.
That's the energy, right? That is our energy. So actually I have the energy multiplied with that standing there. So let's combine that all. And what I also do in those, I mean, a summation index is a dummy index. So I'm always allowed to change the summation index. So instead of having J here and I there, I rather want to have I in both cases, because then I can combine them in the same. And that matrix element and that matrix element, if the wave functions are real, if the determinants are real, those two are actually the same. Because this is the complex conjugate of this one. Turnover rule, Hermitian operator, so the Hermitian adjoint is the same as the operator. And the complex conjugate disappears because they're real functions. So this is the same. So I end then up in having this sum plus that sum. That gives us 2. So I get the derivative is then equals to 2 times sum over AI, and then phi I Hamiltonian, which one do I want to use? No, I take the other one. Phi I here, and here I have k. Remember I took the derivative, it's all taking the derivative with respect to k. Still divided by the sum over those, and then I get minus here, minus 2 times AK times the energy. That's this part, that, and the energy. And since we're trying to find the minimum, or at least a stationary point, we set that equal to 0. Now, that is the equation which we get if we take the derivative with respect to one of the coefficients. But there are many coefficients, as many as we have determinants up there. So I get many equations, and I can stuff them sort of, write them one below the other one, and I can make a big matrix out of that. I can make a matrix equation out of that, where each row in that matrix equation corresponds to the derivative with respect to one of the coefficients. So what do we have? We have here, so that's the row index. That's the reason why I want to have it standing first. So for each AK I get one equation. So if I put them in the row of my matrix, this is the row index. And I have a sum over all those. So that's going to be the columns in my matrix. So I have here, I have this integral over the Hamiltonian with 2 Slater determinants is then an element of this matrix. This is the Ki element of the Hamiltonian matrix. The Ci Hamiltonian matrix. So I have this matrix here. I get rid of the 2. That's doesn't matter. I can multiply the numerator over there, and also goes away. But I said let's get rid of those, and let's get rid of those right now until we. So what do I have? I have this multiplied with those coefficients. So I need a vector of those coefficients, and whether I multiply them from the left or the right, well, actually it makes a difference because that I is here. So if I want to write it a matrix times a vector, it actually has to stand behind them. Otherwise I don't get that. Because this is an element of a matrix, this is the element of a vector, so the vector has to stand behind it. Then I have this thing here. Here I have only a particular one, but I still want to squeeze it in my matrix, so I better write the energy times a unit matrix. And that's the zero vector. So what we did, like always, we ended up in a matrix equation. So we have that big matrix, we have to find the eigenvectors, which means we have to diagonalize that matrix and find the eigenvalues, which are going to be the energies, and the eigenvectors are going to be the coefficients. And that is sort of what is called configuration interaction, also called CI.